Minister of Education, Science and Culture, dear guests, my name is Sigurður Magnús Garðarsson and I'm the chairman of GEORG, and it's a great pleasure for me to welcome you to the second GEORG Geothermal workshop, which is organized by GEORG, the Geothermal Research Cluster. As many of you know, GEORG was established in 2009 with the support by the Science and Technology Policy Council in Iceland through the Centers of Excellence and Research Cluster Program, what we call MARC áætlun in Icelandic. And it was supported for 7 years. And last night I looked up the first minutes from our first board meeting, and it is dated 18th of February 2009. So we will be celebrating 10 years next February. You are all invited. So we can say that this has been a successful run for the last 10 years, and we plan on going strong onwards. And we are actually involved in many interesting projects, including the workshop, of course, today, and also several Horizon 2020 projects, and also the Krafla magma project that we are currently developing. And we actually had 2 days workshop yesterday and the day before yesterday, Monday and Tuesday, working on those issues. And some of you that are in the room here today were with us developing that. So there are exciting things going on. The workshop today and tomorrow has a lot of interesting talks and activities, and I would especially like to thank our sponsors. We have the logos up here. It's Reykjavík Energy, Landsvirkjun, HS Orka, and Orkustofnun, and their support is highly appreciated. I would also like to just remind you that we have the schedule in an app, so I guess all of you have your phones and you have hopefully downloaded the app, and the schedule is there for the conference. Our keynote speakers in these sessions are 3, as you can see up here. First we have our minister coming and saying a few words. Then John Lydon, the Executive Director of the British Geological Survey. And finally we have Ingólfur Þorbjörnsson, which is the head of Geothermal Engineering at ISOR. So with that, I would like to welcome to the podium our Minister of Science, Lilja Dögg ALFREÐSDÓTTIR. Please.
Dear guests, it's a great pleasure to be with you here today and to open the GEORG Geothermal Workshop for 2018. The GEORG Geothermal Research Cluster is a prime example on how strategic national funding of excellent innovation ideas can result in multiple interdisciplinary and international research projects, start-up companies, and related activities which attract large grants from international programs. In my opening address, I'm going to give a short overview of the government's policy as regards to science and technology and how GEORG has been built up in connection with that. And I can tell you that the Icelandic authorities are extremely proud of GEORG and how the science and technology community in Iceland has been able to support the build-up. In 2008, the Science and Technology Policy Council initiated a top-down funding program based on research and innovation priorities defined in the Council's policy for 2006 to 2009. The Strategic Research Program for Centers of Excellence and Research Clusters was based on priorities that have been collected through wide consultation where people from various backgrounds discussed the main challenges facing Icelandic society. This work initially resulted in the Science and Technology Policy Council's resolution published in December 2007. The Council's objective with strategic program was to support and spur scientific and technological research, encouraging cooperation between different actors and promote values, creation and investment in research and social and economic development. The strategic funding program received 83 proposals for the first application stage, which I think is pretty extraordinary for a society that only counts around 350,000 people. Only 10 of those were invited to send in an application for the second stage, and GEORG was one of the 3 projects selected for the funding. The story of GEORG is a story of success. GEORG builds on an already existing knowledge base accumulated through decades of utilizing and studying one of our most valuable national resources, geothermal energy. GEORG's strength lies in bringing together people from different sectors, including main Icelandic educational and research organization, energy companies, energy firms, and startups in geothermal science and utilization, as well as international cooperation. GEORG has supported over 30 research projects. A large number of graduate students and postdocs has resulted in a large number of publications, which we are extremely proud of. To date, the total turnover of GEORG activities is more than 11 million euros, and it has played a major role in shaping the European research and innovation agenda with geothermal energy. Dear guests, the world today is facing numerous grand challenges. At the Ministry of Education, Science and Cultures, we are in the last phase of defining the most important challenges for Iceland in the coming years. GEORG is already taking on one of the biggest challenges of modern society faces, reducing worldwide emission for greenhouse gases. Due to the environmental conditions and history, Iceland is at the forefront of research on and the use of renewable energy resources, where GEORG plays a major role in making Iceland a case study for near energy-dependent and carbon-neutral society. The Icelandic government is currently devising a national roadmap for research infrastructure, and several actions in the Science and Technology Policy Council strategy are aimed at improving the Icelandic research infrastructure ecosystem. The ministry monitors with interest the progress of the setup of Krafla Magna testbed, a groundbreaking research infrastructure plant on the surface of Krafla volcano, making possible sampling of magma from the Earth's crust. Finally, the Science and Technology Policy Council launched a new strategy research and development program this fall. This time focusing on language technology. We hope that it can do the same for the sector as the initial strategic funding did for GEORG and its associated research and programs. There are those who are skeptic towards strategic funding and prefer all government funding to be allocated through a bottom-up approach used by large competitive firms nationally and internationally. And yes, we can agree that for the sake of free science, a bottom-up approach based on peer review of scientific excellence is essential to maintain and nurture a vibrant and viable research community. On the other hand, I believe that the well-defined top-down strategic programs with clear goals can lay the foundation for cooperation between and within sectors that previously was not possible. This in turn facilitates the forming of critical mass with its added value necessary to create opportunities not possible with traditional bottom-up funding. If projects like GEORG are on the receiving end of a strategic finance, it's definitely money well spent. I wish you all the success for this workshop. It's extremely important that we have all key policymakers, scientists, everyone basically here that are in the room have gatherings like this, and we can see, you know, what is the value added. In my mind, it's without a doubt how successful GEORG has been. So everything that gives me greater arguments to argue for greater funding as regards to scientific research and innovation, please bring it on. Thank you very much.
Thank you, Lilja, and thank you for your kind words and also the encouragement. It's highly appreciated. Next, I will invite to the podium John Lydon, which is the Executive Director of the British Geological Survey. And he has been here since the weekend, I guess, and working with us on developing the Krafla Magma testbed project. And we are very much thankful for your time coming here, John, and giving us input and a valuable resource in developing that project. So that is very much appreciated on our behalf. And so please step to the podium and give your speech. Thank you.
Is my speech there somewhere? I just click on it. I think I just clicked away. Yeah? Okay. Okay, good. All right, lovely, thank you. Thank you very much for inviting me, and thank you, Minister, for that support for geothermal and for GEORG in general. I think it's GEORG is an excellent initiative in the tying up between research and industry and government. I think is an example of how those things should happen. So what I've got to do is give you a talk on my view of where kind of I think geoscience is going in general. It's not necessarily a geothermal talk. It's some reflections, and it's kind of based on me. I ran a geological survey, which is we have about 700 people, but I also used to be head of Earth Sciences research in France, and I kind of worked around the world a bit. And I used to work in the academic world and the government world and the sort of survey world. So I kind of got some sort of I kind of feel I should be talking to you, and I was behind the bloody. So anyway, so the talk's called "Where is Geoscience Going Anyway?" You know, with a comma anyway. So it's my view, but I think you'll probably find that a lot of people are actually starting to trend this way, and it's where we think the science is going. And so the first slide is sort of what is geoscience anyway? What's it for? I'm not going to read all this for you, but there are some headers there. So clearly geoscience has always been for understanding how the Earth works out, the motor of the Earth, the dynamic Earth. You guys here in Iceland live with it, so you feel it every day, literally actually. It's here to create a safe and a healthy planet, so minimize the effect of natural hazards, building cleaner and sustainable environments, and living sustainably on the planet. So in particular, for providing the foundation for responsible use of resources going forward. Driving growth. I think often we forget that geosciences are essential in driving growth across the world, not just in the traditional minerals and resources, but in infrastructure, in building, and these sorts of things as well. So, and essentially reducing global inequalities and supporting science and capacity building in developing nations. And I know that ISOR, for example, does do a lot of work overseas in the geothermal world. BGS does as well, and there's potential there to really make a difference in, for example, Africa in the provision of power and energy. So, is the need for geoscience as we know it changing? And I guess my comment is yes. So are we prepared for the new drivers in our science? Are we content with an incremental knowledge? I mean, that's a very kind of negative thing to say, and sometimes when I give this talk, the academics say, oh, you can't say that, but I think you could argue that we've done a lot in terms of environmental and other science. We've decided that we've proven to the public that there are severe problems around climate change and planetary change, right? The question really is, so what are you going to do about them now? What are we going to, so we need to think about that. Are we teaching the right subjects to students? Are we sure that we're preparing our students for work, communicating with the public on key issues, and are we living up to government's expectations, right? And promoting global science and energy. So those are sort of questions you should ask yourselves, and any science area should ask yourself that really. But there are some new drivers, specifically I would say for geoscience, but also for science in general. So the diversification of energy supplies and essentially decarbonization. So in my geological survey, where I would have normally said we have an energy group working with oil and gas and minerals and stuff, that group is now called decarbonization. The focus is how can we decarbonize the planet, knowing that we do also have to continue consuming gas and such like for going forward. It's a process. Reducing emissions of CO2, methane and such like. I think there's a shift towards understanding the risk rather than the hazard. So in general, in geosciences, we tended to focus on the risk because it was the interesting bit. The less interesting scientifically bit is the risk, but it's clearly the most important bit. You know, how do these hazards affect people and how can we manage that better? Global population change and open and big data and information science. Right? You in Iceland are clearly involved in that. You actually probably have a potential in storing data, I think, going forward, because given your climate and such like. But it's a very big driver for geosciences, as you'll see. And I think the last one here, which is I think the most difficult challenge that we have as a bunch of geoscientists on the planet at the moment, these people who are trying to develop new energy systems or even build highways or even build rail lines, HS2 in the UK, is dealing with environmental regulation and greater public scrutiny in general. It's a major, major problem that we need to deal with. It's probably a valid problem that we're being scrutinized, but you know, it becomes quite challenging sometimes. So there are still big questions out there, and you know, we shouldn't say to ourselves, let's stop focusing on the really big questions and let's stop doing, you know, really important discovery science. I think they're out there. And these ones come from the 125th Science Anniversary compilation. How do planets form? What cause ice ages? Mass extinctions? Why does the magnetic field on the planet reverse? We don't really know that yet. And you know, can we actually predict volcanic eruptions? You know, what are the precursors and can we model them? And that's sort of part of what the Krafler thing's all about. So I think we can be fairly confident that discovery science, as we call it in the UK, I think you may call it that here as well, is still important, still needs to be funded. I would argue probably the balance between discovery science and the more applied science or the more solution-based science needs to shift. And so you could ask yourself, sort of, maybe not in this audience, because it's quite an applied geoscience audience here, but do geoscientists undertake and value applied research? You know, do we focus a little bit too much on the discovery and not the translation through to impact? A question. So this picture here is not a geoscience picture, but it's a picture of not very clear either. You get the feeling it's a tree. It's a tree that is instrumented to death. We're measuring the vital signs of that, on that tree. We're measuring its temperature, pH, EH, photosynthesis, how many bugs there are. Everything you can imagine is being measured on that tree. And so we've been doing that for some time in the ecosystem world above ground. And I think the big shift is that actually we can now turn that tree upside down and we can start to do that underground. And we need to do that underground to be able to reassure the public that we know what we're doing down there in many of these things. So there are some pretty big drivers for our geoscience at the moment. Underground sensors, many of you here are involved in underground sensing technology. That they're getting smaller, they're getting more effective, they can go to higher temperatures, they can go to more acidic conditions and such like, so you can do things underground with sort of a throwaway sort of sensor technology we couldn't do before. You can throw sensors down volcanoes, see what happens. You know, you can use drones. There's a lot going on in that world, as we know. There's a lot going on in the visualization world. So how do you visualize things? How can you stream things real time? How can you get stuff to the public rapidly? And then big computing. So clearly that is a major change, the shift that we're going into in terms of artificial intelligence, data mining. And you could argue that actually that at some point a computer will be able to produce a better geological map than we can. Right? My staff don't like that, but you could argue that. So these things are driving the future of our science. And I think there's a really big shift towards real-time data. And I think in Iceland you do that quite a lot. But streaming data real-time, this is a project that we have in the UK where we're putting in 2 big underground facilities, looking at geothermal, one of them, shallow geothermal in Glasgow, but also looking at fracking and various other sorts of potential subsurface activities in the UK. So streaming real time, making sure that the public can have this data on in their kitchen tables. So kind of a little comment, we've been doing this up in northern Yorkshire for about the past 2 years to prepare the baseline for methane for potential fracking operations. So we're informing the public. We were wondering whether or not anyone was even looking at this stuff, because you're streaming it real time. And then about Christmas time, one of our staff was up there and they dropped a metal pylon on one of our methane flux measuring systems, and a methane spike, well, not a methane spike, but an electronic spike went out immediately. The Twitter sphere went wild within 20 minutes, right? So that was good, because that kind of said, well, actually someone is looking at this stuff, right? Even though, so that was a good example of that things are different. The world's different, the world's watching us at the moment. So a lot of the solutions to decarbonizing the planet are geological. Right? And there's some up here. I mean, there's radioactive, or dealing with nuclear energy and dealing with the waste from that. You may or may not be aware of it, but the Dutch have voted last week to reopen discussions around nuclear energy, using nuclear energy. It's clear that you're going to need a base load of some kind, even if you move towards more and more renewables. You need some sort of base load, and nuclear is potentially that base load. In the UK, I think we think so. Shale gas, like it or dislike it, I'm not saying that I do, but it does. If you replace coal with shale, you are decarbonizing the planet to an extent, and we do need to keep supplies of gas going for the future. And even if the gas is used actually for producing plastics, we still need the gas. So it's there. Geothermal. I say no more about geothermal. You guys are quite fervent leaders in the geothermal world, but even then, the geothermal is something like 0.5% of the total energy mix globally. So can we get it up to 5%, or or do you do it in areas where it really makes sense to do that? Carbon capture and storage is back on the agenda in the UK. I think it went off the agenda, but it's coming back on the agenda. Certainly, carbon capture and utilization, sort of using the carbon if you can, is coming back on the agenda. So if you can get away without storing it and can use it intelligently, why not? One of the biggest shifts that I see at the moment is actually underground energy storage. So compressed air storage underground is one, and also hydrogen storage as we move towards a hydrogen economy. I think we will move towards a hydrogen-based economy fairly rapidly. I think the vehicle fleets will shift some of them towards hydrogen as opposed to batteries and such like. So decarbonizing the planet is something that will require us to monitor, to get underground, to do all that possibly. And in your case, in Iceland, you have a fairly low population density, so you have challenges there. But we have an incredibly high population density in the UK, and all of these potential solutions that you see here are all across, mainly across northern England, where there's a large population in Manchester, in Sheffield, and places like this, or Glasgow. So how do you do that? Big question, but a very strong role for geosciences. And then global hazard relative to risk. And going global, this is a map from an initiative called the Global Earthquake Model, where geoscientists are actually working with reinsurers, trying to reduce, they're trying to reduce their premiums, I imagine, but also trying to reduce the risk and the death from earthquakes. For the geologists here, as an aside, it's quite interesting that the red squares here the red squares are actually the historical earthquake catalogue, so the ones that you can track back in history for about 1,000 years, and the yellows and the greens are the active catalogue. So the active catalogue has only been active since about 1960. But interesting, if he hadn't produced this historical catalogue, you wouldn't actually see this earthquake zone going through there. You can see it's actually defined by the historical catalogue. So, trying to understand the risk in those sorts of areas and such like, and a shift to risk away from hazard. So that different sorts of science, sort of where does the fault end up in a city in China, and what will be impacted by that fault? Global population, so that's an African groundwater atlas that actually we produce in BGS, but it's a model. This thing was downloaded tens of thousands of times by all the aid agencies, because the aid agencies think we know where the groundwater is, because we produce this map. But no, it's a model. And so, but it kind of goes to show that actually you do need to know where the groundwater is and to be able to manage the groundwater in Africa as population grows, right? And that's one of the biggest challenges we have. So geoscience research will help provide water, food and health services, better soils, better quality water, better quality agriculture, and it can address urban growth. So a large amount of what we're doing, I think other surveys worldwide are starting to look more and more about urban geology. So we recently produced a subsurface geological map of Singapore, but we're now doing the same thing in Kuala Lumpur and the same thing in Hanoi, but in association with those local governments and local scientists. So coming back to something a bit more esoteric, but actually applied. So I think that Musk will land a car on the moon in the near future, or someone will, and so that will completely open up again the science of petrology, the science of what do rocks look like, right? And I think in our universities we're not training people in that world anymore, because it was kind of a trendy science when I was young, because I used to do it, but it's no longer sort of the top science, and those questions will be asked on the moon. How do you what are the moon rocks made of? What sort of water contents do they have? How do you extract the water from them? So a complete new field of applied mineralogy, I think, will develop once we land on the moon, right? And sort of understanding the model and modeling the Earth. This is the gravity satellite data from GFZ Potsdam, basically from the gravity satellites. And there's a new generation of these satellites that are up there now that will start streaming back in 2022. And with high resolution, you can actually start to predict groundwater trends, where's the groundwater and various things. So a new generation of space science for geosciences. And these are big investments. This gravity satellite, we often say no one puts any money in geoscience. We often say, yeah, we're the underdogs, the space scientists get it all. Actually, 90% of what's done with gravity satellites is geoscience, right? So there is a significant amount of money. And the same goes for magnetic field satellites. Most of what's being done is geoscience. So we do get some of the crumbs now and then. And then global big data. So I'm going to flash onto the next slide in a second, but clearly big data is a challenge for all the sciences at the moment. And where does earth science or where does geoscience fit into that? So we've started to, so there's a bunch of geoscientists, we've started to talk to the climate scientists. Interestingly, it's very hard to talk to climate scientists because they kind of think they were put on the planet to solve the climate problems, and there's no other problems that there are to be solved. Well, it's not strictly true. But so they said, well, we want to, and this is part of one of these big European future emerging technology platforms that we're developing with them called Extreme Earth. But they said, we want to be able to model climate and weather at a 1 kilometer resolution, right, going forward. And to do that, we need better computers, and we need, actually then it's not about computers, it's about algorithms. You need better algorithms. Because the climate modelers are still running models that are based on Fortran programs 30, 40 years ago. And then you run a program, you stop, you run a program, you stop. What they want is a real-time program that you can change as it goes along. And they said to us as scientists, so what can you do that's as good as that? So I got a bunch of seismologists together, one or two of them may be in the room, I'm not sure. And we said we will produce complete seismograms at 10 hertz resolution, right? Which is actually about sort of 50, 60 meters shaking maps. So, and they said, oh, that's pretty good, that's actually better than we can do. But the algorithms and the practices, if you want, are the same. So, so you're using the same sorts of algorithms, the same sorts of technology. So we managed to get those two groups to come together. I'm pretty sure Europe will fund the first phase of the development phase. They'll announce it at the end of the month. I'd be surprised if they didn't. We were number 2 in the initial ranking, so I think that's a good sign. Potentially a 100 million a year project for 10 years, right? So really big money put into our sector, but along with the climate scientists. And then, so why would you do that? So you've got these high-resolution modeling for climate, high-resolution modeling of the Earth, and between that you've got infrastructure, food, agriculture, all the edge computing that joins into that, right? So I think that is the challenge. Can we tie up this sort of high-end computing, bringing in edge computing and such like? And the geothermal would clearly be part of that. The energy systems and such would feed into that. And then, kind of towards the end of this talk here, sort of the question is, I kind of started by saying actually that our science is a little bit too parochial, that we're, I'm an environmental scientist, earth scientist, I kind of love the science, but are we doing enough big things that really will make a difference? Or even big things that will actually allow our funders to sell our science going forward? Because they're competing with the Medical Research Council. And the Medical Research Council will say, look, we're saving people's lives. And they'll say to the earth science funders, what are you doing? And currently earth science funders are essentially saying, we've got a problem, the planet's sick, but they're not saying what they're going to do about it, right? And so the question is, what can you do about it? And that requires us to work with environmental scientists, engineering scientists, and socioeconomic spheres. It requires us to bring all of that together. So 3 examples here. One of them is topical, Krafler, right? Should we drill into a magma body and control the magma fluid system, right? I think we've spent a couple of days thinking we can do that. The implications of that are enormous for energy resources, but also shifting the whole monitoring of volcanoes from the surface down to the magmatic front or the magmatic interface. So a complete new generation of understanding magmas. And the question you can ask is, can we actually stop an eruption at some point? Maybe it's not a silly question. Can you stop something erupting? Because the volumes, even in Iceland, the volume's not big, right? Now you may not want to stop it erupting in Iceland because it attracts tourists, and as long as it's safe, well, why bother? But underneath Naples, right here, right, if we know there's a magma body coming up, if you can see it, can you stop it? Can you freeze it? I think it's not a silly question. Big science, right? Should we undertake a fully researched hydrofrac? Now, the UK, we're going in that direction. There's not yet been what I would call a fully researched hydrofrac in the States, right? So really understanding what's going on there so you can improve the technology. And then for the more environmental people, are there ways of paleontologists? Our paleontologists love looking at rocks that are 300 million years old, where tons of carbonate was being dumped into the oceans and such like. Or the coral reefs, the chalk cliffs of Dover, right, which are Cretaceous. All this carbonate coming out. Can we actually use that knowledge that we know there now to actually modify how reefs grow, right? Instead of saying, well, this is what it used to look like, and not really trying to apply that knowledge. Then, so there are a couple of challenges, as I said. That is there an inherent arrogance with respect to applied problems? I think there is, certainly in the academic world, less so in the applied world. Are we too focused on the Earth's history, what it used to look like, as opposed to what it will look like, right? And I say yes, we still need to look at what it did look like to understand what it will look like, but we should be focused on what it will look like. Should we be solving the environmental problems rather than just identifying them? Yeah, we need to shift to that. And then where is the big Earth science? Where are the big Earth science questions, the moon shots or the astronomy type shots that we can do? I talked about skills shortages. I won't go into that. I think I gave you an example for minerals, but you could ask for in the whole fluid world that we're working in terms of fluids underground. We need special people for that. So, although we're scientists and often respected scientists, we're actually viewed as well as part of the problem, because how do we communicate this and how do we get our message across? And you must have the same problem in Iceland. I know you do. We have it in spades in the UK at the moment, so this is not the UK, this is probably Germany, I think. No, maybe not. No, that would be the UK for nuclear waste, radioactive waste. Carbon capture and storage in Germany. This is a blowout. It's from a film where the CO2 system blows up in the Netherlands. And the public see this and they get really concerned. We even have, this is the most amusing one I think, which is get the frack out of Sussex. But it's, the companies were not even fracking there actually, but the community thought they were. And so, how do we engage with these? So the 2 underground facilities that we're putting in the UK, we spent a lot of effort engaging with the communities, out there talking to them all the time. And it's a really important. I know that in Krafler we started doing that, but it's a very important part of what we do as scientists. So I think the challenges that we have are in communication with the government and public are better links with socioeconomic research. We have different cultures, different schedules, different opportunities. We have conflicting messages. We have to fight public perception. I think in general for our science in the programs we need continued but more targeted discovery science. We don't need a sort of shotgun approach to discovery science, so we do need more top-down, as you said, Minister. I think that, you know, this balance between top-down and bottom-up is an important one. And we, in the UK, in the UK we're pretty much all bottom-up, and I think that needs to shift. I need to explicitly address global geoscience problems and provide solutions. We got a planet that's sick. How are we going to fix it? Not just it's sick, we'll find something else that's sick about it. You know, it needs to be, you know, really moving towards solutions. And I think we need some extreme geoscience flagship projects to help us sell our science and to help our ministers or to help our funders actually take the science and say, look, we're doing good stuff. And Krafla is one of them. I gave you some other examples as well. And to finish, we love Iceland. Our BGS geologists enjoy coming here. Sometimes I discover that they're up here without me knowing they're up here, spending money they probably shouldn't be spending. But anyway, it's a wonderful place to work. Thanks very much.
So thank you, John, for your presentation, and thank you, Lilja, for giving you time to stop by this morning. I appreciate that. Next, we have Ingólfur ÞORBJÖRNSSON, which is the head of geothermal engineering at ISOR, and he will be talking about activities in the geothermal field. Ingólfur, please.
Yes, good morning to you all, and I want to go a little bit more local than my predecessor here. I want to talk to you about how we can get into the resources we have down Earth, and a little bit about the experience we have had with that and why we need some innovation in doing so. It is very clear to those who are working with the geothermal energy that this is today a competitive energy resource, but it's the wind, solar, and bio is coming very close. So we have to be very careful that we stick to the fact that economic reasons is the driving force for this, and we need to optimize the use of the resources, both the natural resources and actually the constructions we do. So that's why I'm talking to you about innovation, about getting the wells to operate for a longer time, the geothermal wells, which we drill down to the high temperatures and takes out the steam or the fluid. Today we see in Iceland and in most countries that the geothermal well, high temperature geothermal well, is in the range of $5–6 million. And if you lose a well because it fails or something structural damages, you have to drill another one and you don't produce in the meantime. So we need something who can help us to go down, and actually the techniques we have been using has been validated for over 30–40 years in Iceland. The oldest wells still used, and we have been quite successful with using these technology and with good results in most cases, but the temperature is rising. And that's mainly because we are going down to deeper origin of the geothermal steam. We are reaching into higher temperatures, and we want to utilize more energy from it. So the ITTP 1 and 2 has been very good examples of this, and we look forward to the ITTP 3, which we hope will manage to do some well where we can operate for a longer time. But today, both ITTP 1 and ITTP 2 are destroyed because of structural damages, and that's where actually we come in with this thinking. Everybody who has been to a high temperature geothermal plant, they know that we actually plan on the surface for thermal expansion. We have these big thermal expansion loops. This is one of the reasons why we have the steam pipes on the surface, so that we can compensate for the metal in the pipes to expand when it's heated up. But we still, after 30, 40 years of exploration with geothermal, we still drill wells where we actually cement them in, and we have them as a straight lines down 2, 3, 4 kilometers down, and we actually lock every movement of the steel in the well. That means that we don't take any thermal compensation on the wells. We just stick to the hope that this will go well. And we tried different methods. We heat it up slowly, and we tried to prevent them from cooling down again. But in many cases, we have learned by the hard fact that the physics and the material properties are quite the same for the material we put downhole as the material we have on the surface. But we don't compensate for the thermal expansion. And sadly, in many cases, we have these damages on the casings, and the casing is the pipe going down in the wellbore. So actually we have these casings failed because of the thermal expansion. We have some buckling in it, as you see, or if we, and this is due to the warm up of the well, and if we have to cool it down again, the result is that we actually have multiple or single damages in the well, where the threads in the connectors, they just go out. So we have this big problem for us that this is both a safety risk, this is operational risk, it's actually preventing any logging or monitoring in the well. This is preventing us to actually safely operate the well if the damages is high up. So this risk has caused both the pictures you see now is from ITTP1, and we know for sure that ITTP2 is as well with some structural damages. So high temperatures means more damages to the wells. Recent studies done at ISOR show us that if you go about 300 degrees and try to extract that energy, the probability of getting failures in the well is ranging from 10 to 50, 60% of the wells. So this is a lot of money in stake, and if we can have some things who can help us with compensating for this, it would be really beneficial for the use of the geothermal. And that's why we have been in ThinkBox in ISOR, thinking about how we can actually compensate for these thermal expansions and allow the metal going down to expand as it has to do. If it is not allowed, it builds up stresses, and the stresses can cause displacement in the metal or some buckling, as I showed you before. And the thing is, can we construct something who can allow the displacement of the metal and prevent that from the plasticity, so that we can use the same design and same manufacturing standards as used up on the surface, downhole. So we have been thinking about this, and we want to do it in the way that this can be actually sustainable for 30, 40 years. So it has to be able to both prevent the warm-up damages and as well if we need to cool it down again, the well. So the thinking is to operate the well just like any other mechanical constructions we have. That's why we have come up with the idea of the flexible couplings. And the flexible couplings is allowing the casing segments to move. So the straight line we have in the wellbore, the pipes going down, is now possibly allowed to move. So this takes out the high load, and this hopefully help us to actually compensate for the losses we have. So in principle, it's very simple. You make connectors who can actually help the coupling that can help the casing to move. And during the movements, it takes up some load, close down, and then open again due to the fact if you are warming up or if you are cooling down. And this is taken up by every 12-meter section. This is built out by pipes who are 12 meters in length. So this is all the same procedures, all the same standards as used today, the same drill rigs, the same cementing job, everything. But now it is possible to take and to make displacement of the casings. So what we have tested is all kinds of loads this can be put into when it's running into the well, both before cementing, during cementing, and most important to operational loads. So we hope that this innovation is helping us a step ahead. And one of the things is that we have been testing this together with our partners in GeoWell project in Norway in 2 institutes, in Norse in Stavanger on the left, and in Sintef in Trondheim in the right. And we have tested 4 full-size couplings, and this has shown us that, of course, there are some room for improvements, but in a nutshell, it's showing us that we can now, for the first time, have a construction who can withstand these high temperatures and the bigger length or increased length of the casing segments we put down. And these couplings have now been tested up to pressures of 165 bars, but in ambient temperature. And of course, we have been looking into running it in whole and see what we can get out of it. So, in a nutshell, we have a design of the geothermal wells today that is actually not good for preventing losses. If we manage to get up a well with higher temperatures, we don't want to shut it down again, because then we know that we can, there is a high risk of damages. So we can't operate this wells in the same way as we are doing in the surface. So we have to think about how we can actually, if something happens and we need to shut it down, the system that can help us, and actually this flexible couplings I briefly introduced to you today is helping us on the way. So it is very clear from our minds that this is something that can help us on the way to get into higher temperature, into magma or to supercritical, superheated steam. But it surely, it's not our intention to talk about that this is the solution, but it's probably a good part of the solution. And by that, I say thank you.
Thank you, Ingólfur. We are now to the end of the opening session, and so we are ready for our coffee break. Following the coffee break, we will break it into 2 parallel sessions, and if I understand it correctly, we will put a wall here, I guess, and be in these 2 rooms. So please look at the schedule and pick whichever is your favorite, I guess. So please, coffee break. Thank you.